So thanks everybody for joining here this first day of March. I've heard rumors that March is going to come in like a lion, but maybe that's just till later this evening that it's supposed to rain a little bit. But anyways, for today we have I call you recently hired, not newly hired, because you've been here for at least a year or so.
December,
okay.
so 3 months.
Really? Okay. Well, it felt like yes. Okay. Maybe I think some of the thing too is I think there were some thoughts that I think I'd heard that you were coming for a while kind of thing. So yes, I guess more newly hired, Dr. Austin Phoenix, who is more based in the National Security Institute, but also is teaching a aerospace and ocean engineering course that we were talking about with American Methods. But for today, talking through a topic of something that be really interesting because we do CubeSat projects here at Virginia Tech. And what's the thermal kind of maybe loopholes?
Yeah.
About it. So without further ado,
Awesome. Well, can everyone hear me? Okay. I'm not blowing anyone's eardrums out.
Sounds good to me.
Awesome. Thank you, John. All right. So today I'm going to be talking about a wild concept, run you through it, and then talk a little bit more about some kind of large-scale thermal control methodologies that are applied to kind of the big expensive satellites and how they don't necessarily fit into that CubeSat model and how this one may be a valuable tool within that space. So without that, we'll dive in. This is kind of a quick snapshot of my accomplishments as an engineer, at least some of them. I've spent a good bit of time building some DoD satellites and have research in a wide number of application spaces, but effectively it's really one method where I take some finite element model of a structure, I deform it in some way and use that deformation to change how it interacts with the environment, whether that be to propel water, whether that be to align multiple optics to build a satellite for imaging capabilities, adapting to change the aerodynamics, or in this case, what we're going to be focusing on today, which is CubeSat thermal control. So without that further ado, we can just kind of dive right in. This is that rough outline of some general thermal metamaterials. Given the audience of this, we'll just touch on that, as well as kind of how you integrate into a satellite and some conclusions. All right, so we're looking at this adaptive thermal metamaterials. What does that mean? Well, so in this context, thermal material is thrown around a lot, but what we want is a thermal metamaterial where it will change its thermal conductivity as a function of temperature. And we want that to basically build a material that will adapt to its local thermal environment. And then the second piece is we really want to be able to demonstrate an extremely large variation in that thermal conductivity. And we'll discuss the impacts of that later, and then have some precision temperature set points that we can do. And then we want to build and quantify the performance of these materials. That's really where our basis is. And so this is really what we're talking about. So this is an oversimplification of thermal engineering, to say the very least, but they're really kind of conventional materials that all exist along this line, where for all intents and purposes over engineering temperature ranges, their maximum and minimum thermal conductivity are effectively the same thing. Copper is effectively a flat line across any engineering range that we care about. And so they all exist there. Then there's this subset of materials that I'll call active materials. And these are systems that somehow change their dynamics such that they have a variation in thermal conductivity as a function of temperature or pressure or some other outside influence. So the attempt here is to get into this range where we're reaching into those thermal materials, be that copper or diamond, or maybe even some of the crazier things like heat pipes up at that upper left. But it can act as both a thermal material and then a really high-end insulator, because in a lot of systems in our life, we have these two states that we need to survive, and we end up having to choose the high temperature state and not the insulator state. So the concept here is can I build this? And so what you see on here is the nonlinear thermal conductivity of copper as a function of temperature, which at this scale looks exactly flat. But can I build a metamaterial and sacrifice some of that thermal conductivity at the high end to build in this kind of intermediate step range of thermal conductivity and then this very low step range of thermal conductivity. And the concept here is, if I want my system to operate between about 20 and call it 55 degrees C, and I implement this thermal metamaterial into that thermal path, then it will self-regulate the system. As the system cools itself, we will reject less energy to the environment, and then as it heats up, we will reject more energy into the environment, enabling a passive cooling cycle into the system. So we'll discuss how I can generate a material that looks like that in later slides. That's really the intent, and the hope is that we could actually build, manufacture, and test these systems and demonstrate them into that metamaterial concept in this slide on the left. So really, there are three different methods that exist out there for building these kinds of metamaterials: contact-based systems, phase change systems, and fluid flow systems. While there's some really interesting things to be said about phase change systems and fluid flow systems, we're not going to deal too much in that space today, and really going to focus on this contact-based system. So as you can see here, this is our classic thermal conductivity equation. And so really what we're going to do is we're going to take a system, and we're not going to inherently change its material properties so that its thermal conductivity changes. But we're going to build an architectured metamaterial that effectively changes the cross-sectional area and the length of the thermal path by inducing contact. So the idea here is we have a circuitous method. So this is the classic example of this that's flown multiple times in a lot of NASA missions for a lot of lunar and Mars rovers, where we have some initial state where there's a small thermal path area, in this case through that flexible rod. We have some conditions where it turns on, and then that contact is introduced, a much larger thermal area is generated, and more thermal conductivity, effective thermal conductivity of that system goes up as a function of that increase in area. And so this is great. You can have a fairly large increase in that area, have a lot of control. But where things start to get interesting is when I make that path much more circuitous or serpentine. And then I take this conventional unloaded effective state on the left with a fairly large delta T across it, because it's having to pass through a relatively small area and a long length. And then I compress it and introduce internal contact within that system. And now my effective area has gone up by maybe an order of magnitude, and my length has gone down by maybe several orders of magnitude. So that's the concept here that we're going to do. And this idea is really there to enable what is a critical case in spacecraft, which is I have some cases where I'm hot, and I have cases where I really need to operate in a cold state. How do I balance those two critical conditions? So this is a 2D version of that concept, extrapolated out, where I have basically a two-material system where I use flat copper plates and then some local epoxy, which is a slightly less thermal conductivity, though this could all be made out of copper and have a very similar effective capability. Now, what gets interesting is in A and B, you see a kind of a flat plate configuration. Once I start inducing distortions in those plates, as I introduce a loading on that system, I can then control and vary that thermal path area as a function of that pressure, and that gives me a lot of control knobs to start playing with. And in this analysis, we're going to ignore convection, we're going to ignore radiation and contact resistance, though those are accounted for later, and we're going to play with linear material properties, which is kind of critical to this. But in this conventional flat plate state, I have now this ability to introduce two thermal conductivities that exist at a temperature, and at that temperature, I would activate the system, apply some external force to it, and close that system and introduce a new thermal path, right? So in that upper graph, the thermal energy has to pass through each of those kind of flexures on the outside before it can actually pass all the way through the system. But things start to get a lot more interesting as I introduce this wave condition. So as I apply loading, there's no contact in between these systems. I apply a loading to that system. And there's the delta T that I can apply across it for a certain case and the effective conductivity. And then I can start loading this system up with a pressure load on either side and generating that contact and progressively increasing that thermal conductivity until I introduce full contact, which generates that higher conductivity and a variable stiffness. And then I can plot this as a function of thermal conductivity versus contact length. and then the stiffness is a function of contact length, and then generate a thermal conductivity as a function of applied external force on the system. So that's really only the first step in the process. The next step is generating some force as a function of temperature. In this case, you can use shape memory alloys, which are a little more flexible for this application, but you can also use CTE mismatch as an application, which is commonly used in kind of the thermal switches that are applied to some of those NASA systems. And effectively, all we're doing here is miniaturizing and making a multi-stacked thermal switch that we can design those activation temperatures on independently. Moving on, we can then take this thermal conductivity as applied force, and then we can generate some applied force as a function of temperature, and that can generate this thermal conductivity as a function of temperature plot that you see here. Some CTE analysis was done to generate this applied force, but we won't really dive into that, as I think shape memory alloys are more applicable in this application, but in any case. So now we have this system and we have these three regions. Region 1 is below 20 degrees C. It's our low conductivity region, and we have some design knobs that we can use to help design it. It's a function of that second thermal path, which is a function of the geometry of the material, and that radiative path, that surface emissivity, and the number of stacks in that system. So we're able to tune and design that number based on whatever we want. This intermediate region is really where you go from that initial contact towards full contact based on the geometry and the other parameters of interest. Then you have this high conductivity region, which is really going to be just a contact-based system. So as we look at that, here's where we can spend a little bit more of our time talking about CubeSats and the thermal environment that they undergo. So in a conventional system with a copper interface between your satellite and your radiator, your conductive path is effectively this, huge pipe that's funneling energy out for that really hot case. So this is, if I plan on operating for, say, a 5-year mission, which may not be the CubeSat example, but if I'm operating for a long time, I'm going to find that worst case thermal environment, that highest case generated heat load, that worst case solar loading on that system, and I'm going to design that conductive path and that radiator to ensure that I don't overheat my satellite in that condition. Well, the problem is one of the critical pieces in, you call it the national satellite world, is this survival case. So survival case is when some anomaly has occurred to your system and your generated heat basically shuts off. So whether this can be caused by a lot of things, but effectively it's a oh no button, something has gone wrong in our system, and we're no longer able to control the operations of the satellite, and it drops into the safety mode. Well, the problem is that conductive path and that radiator are designed to pull an enormous amount of heat out of that satellite, and very quickly. There are a lot of things that have been done to manage that radiator emission value, right? One being variable emissivity as a function of temperature research that went on for a number of years. There are methods to change the effective area using louvers or other methods, but those are all pretty difficult and don't have a ton of control over that radiative case. So the idea here is basically CubeSats, because of this nature, you have a really short time window to basically intervene in an anomaly of a CubeSat before the system basically cools to the point of death. What I would propose with this system, where I incorporate a metamaterial in that conductive system, I now have reduced that conductivity a little bit. But I still have that same kind of effective system where I've got a hot radiator emitting to space and a large generated heat. And it's important to note that I would have to have heaters to basically maintain the life of that conventional satellite in that survival case. But once I introduce that metamaterial, I no longer need those heaters. I can have a very small amount of generated heat. And what I enable is that radiator to effectively disconnect from my satellite thermally, and then cool down and drop its thermal radiation out to space, which enables me to basically operate theoretically indefinitely, depending on the satellite conditions that I've selected. But this really enables you to drop that effective conductivity by several orders of magnitude, and basically just sit there warm and happy with your electronics within a nice tight window of temperature for a long time. And so what I'm showing here is that by directly controlling that radiator cold temperature, you're able to generate well over an order of magnitude change in the effective heat flux out of your system, and that thereby could save a whole lot of satellites that exist out there at a fairly small mass budget cost. So that's really the idea there. And so we build a thermal model of the system. I won't really harp on it, but these are the thermal inputs to the system. And the real key is to understand how this metamaterial may respond to variable generated heats. So I've tested a couple different cases that we can walk through, but the real key is I have 3 temperatures that I'm tracking here: the satellite bulk temperature, so to speak, my metamaterial temperature, the activation of that, and then the radiator temperature. And then I have to ensure that I capture all those thermal interfaces. This is just a simple MATLAB model that's performed here. So this is really the resulting case. So in the upper left, I'm showing you a low amplitude sinusoid. All right, second try, where you have a generated heat function that varies between 60 and 30 watts. And you can see that in the bottom left, it's got both. I evaluate this input for both the copper interface and for my metamaterial interface. And then at about 140 hours or so of operation, the generated heat goes exactly to 0. And so we can then evaluate that thermal environment. We'll also look at a sinusoid and a random input, where we generate a high amplitude, long duration sinusoid operation, which is, maybe you're doing some science mission that has some long form operation, and so that may generate that generated heat path with a similar cold saturated case. And then I have some random generated input varying between, in this case, call it 5 watts and 55 watts. And so these are the 3 cases, and then the resulting calculated conductivity of my metamaterial and my copper as I sweep through these cases. And it's interesting to note that as in those upper cases, the blue is when it's cold saturated and the red is when it's hot saturated. But this is showing that the thermal metamaterial is changing its conductivity as a function of time to help mitigate some of those thermal swings in our system. And so as we step forward, this is the resulting case. On the left, we have that low amplitude sinusoid, whereas it's a little difficult to see, but in that bottom left, you can see that the copper overshoots of the metamaterial temperature plotted there, and is able to actually maintain its temperature after that survival condition is met, or after that generated heat goes to 0, at a very balmy 20 degrees C for those electronics, enabling basically indefinite operation of that satellite and batteries and all the other things that would result in failure. And it shows here that the metamaterial has a much smaller delta T in the system, which relates to the lifetime of the electronics, which is also a useful metric to track. The high amplitude case is a much more difficult case to survive because of that low generated heat case, or that occurs around 50 hours. But you can see that copper sees an enormous delta T over that time scale. And if any of your electronics or your systems get below, depending on your electronics, mill standard might be minus 15 C, but batteries hate it warmer than that. So one cycle of this might result in death, but your metamaterial is able to survive it. Where the really interesting stuff happens is over there on the right. In the random, if you have highly variable and well understood generated heat, which would be nominal for a mission that's doing things that aren't as orbitally focused, where you're only operating at maybe certain parts of your orbit, you could have a fairly similar case, and it's able to really effectively control that temperature window within the system. And this is all tunable by the design. If I wanted to operate my electronics below 60 C, I could just change those temperature set points in my metamaterial, switch them out with a different shape memory alloy, and enable a different set of thermal conditions for my resulting output. So this is really, an attempt to show that if we just allow our CubeSats to operate nominally, with some large radiator, that they're going to see some large temperature swings, which may be damaging to our system and hard to predict, and not something that students are going to really have the opportunity to study. But this is an interesting way to incorporate it. Furthermore, this is an interesting model that could use some validation effort and data incorporated to it. It may be a useful tool for next, CubeSat modeling to take this as a starting point to evaluate the thermal environment that you'd expect your CubeSat to see by adding a little fidelity into the things like emissivity and other things. Obviously, this could have a huge impact on the lunar Venus environment. When we landed people on the moon, it's a surprising fact. We've only landed in early morning in the lunar day because noon is brutal and midnight is really scary. Electronics really hate minus 100 C, right? Like it's a tough environment to be in, and so especially given the time duration that might be a month, it really is a difficult environment. So how do we survive both I'm operating at a very high heat generation level at noon and a low heat generation level at midnight? And this could have a way to help solve that with everything in between. Electronics and hypersonics, it's driven both by the external thermal load and internally generated heat. So there's a potential for this there. And then a lot of that thermal management or thermal cooling can drive a lot of our computer energy use. So maybe more localized or focused thermal cooling could be something that this could leverage. But really, this has a lot of potential to do some interesting things. I'm reaching out to NASA to see if they can fund it. We're trying to work with DARPA to actually build some of this hardware and actually then test it. I'd love to put this on a balloon. I think that'd be a really cool project. Get it to that high altitude, get it to that low convective state, and put a heater on it and cycle it a couple times, see what happens. It'll be really fun. And then obviously TVAC chamber and build a couple of variations to do some more focused optimization work. And then I guess the last thing I'll leave you with is I was at work late one night watching a YouTube video, which is maybe not something I would suggest, but in any case, there's this really interesting metamaterial concept that they developed, and they developed an entire kind of architecture around this, where you could print out a hinge or a joint. And in this case, this is a door handle that's a single piece of material. So as a structures person, mostly focused on that part of the problem, I went, man, that's a really interesting problem. You have all these internal contacts. Modeling that would be weird. I wonder how you would thermally model such a weird and complex structure. And I went, I wonder if you could induce contact intentionally to control the thermal flow of energy through a system. And that led me down this rabbit hole to date, and a couple interesting results that are finally to the point where I'm showing the applicability of this rather than the concept, and hopefully we can get some funding to build it and test it. So with that, any questions from the room?
Yeah, still can't get anybody come up here to 6-4.
Yeah, even with the cookies.
Yeah. It's hard to compete though today. I get it because it was what they called they rebranded to Wonderful Wednesday. Usually they do Fun Fridays, but since Friday is the right before the break, they moved it to Wednesday, and they had dozens and dozens of donuts down on the 3rd floor.
Oh, that's a tough one.
Yeah. So hard to compete with that.
It saves on the cookie budget.
Yes.
You just keep bringing the same cookie box every one of these.
Any questions from the Zoom on this?
So I have a question. Can you hear me?
Yep.
Yeah, this is Sui from mechanical engineering. So this is awesome. This is a very cool work. I have a question about this. You're trying to apply this thermal metamaterial to the CubeSat system, and usually you have a pretty strong limitation in terms of space available on the CubeSat. Do you have any? Is that going to be a challenge for you? Because if I guess that how thick should the material be, and do we have enough space in the CubeSat to do something like that?
That's a really good question. Thank you, Dr. Lee. So this initial concept was 1 centimeter thick and was 6 centimeters by 6 centimeters, which was by no means optimized. The cross-sectional area that you need is really just a couple percent, maybe 10 to 20% more than the thermal interface that you have using a conventional radiator connection. So I think the integration challenges of this are fairly small because it can be very thin and lightweight. Now that is going to be a function of your manufacturing tolerances, which is another set of challenges in and of itself. But while the size challenge and weight challenge of this system are real, I think those are pretty manageable, especially given the performance of this metamaterial is more than you would necessarily need. Indefinite operation and survival is probably not actually a reasonable goal. You just want tens of hours rather than minutes of survival. So I think with a tuned system to a CubeSat example, you could get the size down some more. What I worry about a little more is the structural performance of the system and size, weight, and power considerations to how much you'd have to structurally support this system, make it work well. Now, you may be able to pull it out of any structural load path, and then it would be fairly trivial. But there are definitely some, kind of swap design considerations that need to be incorporated into this analysis. Yeah, that's a really good point.
Okay, thank you. Thank you.
Hi, Dr. Phoenix. I have a follow-up question to Dr. Lee. This is Darshil here. So first of all, great presentation. Like, there were really interesting concepts being shared. So the follow-up question is, you talked about the structural load path and taking that into integration. So have you looked into like multi-physics topology optimization concepts where we can optimize both structural as well as thermal path together? So that's my question one. And then second question would be, I work in topology optimization, especially multi-scale topology optimization. So I've seen like tree-like structure to dissipate heat very quickly when it comes to thermal loading. So are there any applications of those kind of structure when it comes to passive thermal devices?
Awesome. So first question, there's an enormous opportunity for topology optimization of the system to co-optimize the structural and thermal performance as a function of temperature. I think that's a really interesting area. Obviously, we're at the point of I applied a sinusoid to the shape distribution, which is about as simple as you can get on that scale of optimization. So I absolutely agree. There's some really interesting areas there. There's some interesting things from a structural perspective you could do that, as long as the system is heavily clamped, it could have really high structural performance. You're not going to have a lot of sliding there and things, but in that open configuration is where you're going to have issues. So there's some ideas I've had about both just tuning your thermal metamaterial for your your hot sunny day in Cape Canaveral, that you're really not worried about the temperature of the system when it launches. Otherwise, you might have to get that topology optimization. As far as the biological system kind of inspired, or the tree-like structure, yeah, that's a really great, interesting example that I haven't seen applied much in space at all. And I think, as we look at really that high performance thermal path that's trying to pump out as much energy as possible, I'm not sure that a radiator that could be integrated into CubeSat would get a ton of performance benefits from that kind of geometry, but it'd be a really interesting place, especially terrestrially, I think, where you can do some interesting things. Or if you're deploying that radiator, then you get to play some really interesting games. Was that a sufficient answer both of those questions?
Yeah, that answers my question. Thank you.
Thank you.
Anything else? I guess one thing I might ask is, so far you kind of presented this as copper. I know one other kind of consideration with CubeSats is the density of the materials, right? If you have because they're more interested. We had an experience where when they're looking at deorbiting parameters, if you have something that's too dense, they won't allow it to fly because they're worried about it not being able to burn up. Has there been kind of thoughts like that about, if you have a stack of copper altogether. Maybe the density of something there is too much.
Yeah, that's absolutely not something that I've thought about for this. That's a really interesting point. I would presume that that since they're plates, that you could treat them separately. Because as it comes back through the atmosphere, there'd be enough tumbling and that they would probably physically separate. And then at which point they're thin plates and not, they're not aerodynamically yet dense. So I think you might be able to get away with it. There are probably some topologies where you'd have to start worrying about how dense it is. And then the other question is, what is that cross-sectional area that you really need to get the job done? Which if you kept it small enough and it was very dense, they're not all that worried about it.
Yeah, but if it's big and it's
they start to get worried. Yeah, I mean, the initial conception was that it'd be an interface plate that's on the order of 1 or 2 inches by 2 inches, which is actually what I think in the thermal in the model of the CubeSat. I think it's a 2 inch by 2 inch cross section thermal path, and so that I think you'd probably get away with because it might be small enough. But that's something. It's a really good point. I hadn't even thought of that.
I guess it's the thinking through. So far, you looked at copper. And there's other plates, other materials that you can, look at that how they.
Copper's kind of in a structural sweet spot because it's low density. It's deforms fairly easily, low stiffness, fairly conformal, but it is a broader look, just like materials would be wise. There's some interesting implications. I mean, copper is also great because you could polish it really easy and do all these nice things. And that polish is really useful. You want to, because that contact resistance can drive that top, your peak conductivity.
Being rough and it's not being in gaps.
Unprocessed copper would be really bad in this application. You'd see huge peak thermal conductivity here. But a lot of other materials are really good at that. Some are really bad. So there's
Cool.
gamesmanship.
Anything else? Always like to give the awkward pause a little bit for people trying to find their Zoom.
Find the mute button.
Where is it? Where's something else?
Well, thanks everyone for their attention. I really appreciate you spending some time with me today.
And everybody enjoy, for those students or whatnot, and as well professors, enjoy spring break next week. Looking forward to maybe having a week without having to get a course together or something like that. And then otherwise, we'll put out that I think there's one seminar, or we only have I think 3 or 4 seminars left, and one of those has already been taken up. I suspect I will have another one possibly from an update from the UpRoSat team. But if you're interested in presenting something here, feel free to email me, and we'll get you on the list and see what you've got going on. And again, the only limitation is just something about space. Anything else? Thanks everybody for joining, and we'll see you in 2 weeks.